In the global effort to combat COVID-19, governments and public health agencies are striving to increase diagnostic testing capacity. The common one-by-one testing approach creates bottlenecks. However, labs have the capability to pull together multiple samples into a single test tube, and that might provide a solution. We suggest strategies for smart sample pooling based on probability, optimization, and information theory. These strategies incorporate knowledge of the expected frequency of positive results, P, and significantly reduce the number of tests and the amount of reagents, equipment, and time required to diagnose huge numbers of samples. This video describes two pooling strategies. In the one-time pooling strategy, multiple samples are pooled into a single batch and tested together. If a batch is found negative, all samples in this batch can be classified as negative, requiring no further tests. If a batch is found positive, all samples in this batch are tested again one by one. This strategy works efficiently when the frequency of positive results is up to 20%. Similarly, in the repeated pooling strategy, multiple samples are pooled into a single batch and tested together. But in this strategy, if a batch is found positive, the samples are split into two halves, repooled, and tested again repeatedly. This strategy is extremely efficient at very low values of P and may be easier to implement in more advanced laboratories. Now, let's apply them in two realistic scenarios. Lab A receives 10 PCR plates for testing. Suppose the expected frequency of positive results is 10%. Testing 960 samples using the naive one-by-one strategy will require 960 tests. Our calculations for the one-time pooling strategy shows that the optimal batch size is 4 when P equals 0.1. Thus, in this example, Lab A divides its samples into 240 batches of 4 samples each and performs one test on each. Approximately 80 batches are expected to test positive, and each of these 320 samples will be retested one by one. Lab A will need to perform 560 tests instead of 960, a 42% reduction. This would allow Lab A to test almost twice the number of samples. In a different scenario, Lab B also receives 10 PCR plates for testing. Now suppose the expected frequency of positive results is much lower, say 2%. To achieve the most informative test, batch sizes should be designed such that the chance of each outcome, either positive or negative, is 50%. Our calculations show that the optimal batch size for this specific case is 32 samples. Thus, Lab B divides its samples into 30 batches of 32 samples each and tests each one. By design, about half of these batches are expected to test negative and can be removed. The positive batches are halved and repooled. Now Lab B tests 30 batches of 16 samples, and here again, they take out all the negative batches and keep dividing the remaining ones. In the next step, Lab B tests 32 batches of 8 samples and then 34 batches of 4 samples each. At this stage, Lab B stops the pooling procedure and tests the remaining 72 samples individually. Lab B performs a total of about 200 tests instead of 960, a reduction of almost 80%. In summary, we offer straightforward, practical, and optimized pooling instructions for laboratories that perform large-scale PCR assays to diagnose the novel coronavirus. For more information, contact us at samplepoolingstrategies@gmail.com.